My name is Roberto Perdisci, and I have Bo here who will help me with the second part of the presentation. So we are presenting JSgraph. This is a system for enabling the reconstruction of web security incidents. So as you know, many, if not most, of security incidents nowadays originate from the web. Take, for example, a web-driven malware infection. And assume that you are interested in watching a recent movie, you Google for it, and you land on a website that offers it for free on streaming. Unfortunately, if you click on the play button of this website, what you get is an alert that covers the original page, and that tells you that in order to be able to watch this movie, you need to update your player. And if you do so, you will end up with malware, unfortunately, instead of the player that will allow you to watch the video. This is a common attack, right? And there are many others, of course, of different nature on the web. And as you know, also, malware infections can have huge consequences, especially in the enterprise world. A simple infection, such as the one that I demonstrated, could spread across an entire network and be the major cause of a data breach, for example. And usually after this type of incidents, which are typically discovered weeks or even months after they were initiated, a forensic investigator is brought in to analyze, well, what happened. And the question is it really possible to reconstruct that attack in details, the origins, the root causes of this attack? And what I mean with that, is it really possible to reconstruct that social engineering attack, for example, that I presented in the previous slide? The challenges for that are the following. Well, first of all, existing logs from the browser, such as the browser cache or navigation history, are sparse, short-lived, provide only limited information about what happened. And even OS logs, well, may not really give you details in terms of what happened inside the browser and what the user saw. Similarly, on the network side, you might have full packet network traces that you have been able to store in, even for a long time. But analyzing network traces is hard if you want to understand exactly what happened inside the browser that generated those traces. And so in reality, to be able to reconstruct web-driven attacks in detail, what we need is a system that can provide more details and persistent web audit logs. So what are the requirements for such a system? So first of all, this system has to run along the browser and be always on. What I mean with that is that it needs to continuously record browsing events, internal to the browser, because attacks are unpredictable and ephemeral, and once they happen, you might not be able to reconstruct them otherwise. Obviously, because this system is always on, it has to be efficient, and it has to have minimal impact on browser usability. Also, we say that it has the web audit logging system has to have no functional interference. What we mean with this is that it should not alter in any way the browser's architecture or functionalities. The system also should be transparent to the user, meaning that the user should do nothing, essentially, to record the logs. The browser should do it transparently. And also, we'd like to have limited storage overhead, because, as I mentioned earlier, attacks may be, or incidents may be discovered much later than the attack actually initially occurred. And so you might need to go back in time by a lot to be able to precisely reconstruct where say, a malware infection occurred. So last year at this conference, we presented a work called ChromePeak that tries to meet those requirements. And what ChromePeak did was to take what we called synchronous web shots at every meaningful interaction between the user and web pages. And so essentially, a web shot is a combination of a synchronous screenshot. So the screenshot is a visual, of course, screenshot of what is actually rendered by the browser. And this is taken synchronously with the user input, so that there is a guarantee that no JavaScript can alter the page before we log what actually happened. And we also similarly take a deep DOM snapshot to have a representation of the state of the page. Unfortunately, one of the main limitations of Chrome Peak is that in between user actions, it does not record anything. We did this for performance reasons. And so now the question is, well, what if there is an attack that is, as it's commonly done, built using JavaScript, malicious JavaScript executions? Well, can we continuously record also in between user actions without having a large performance overhead? Well, that's what JSgraph is all about. And what it does, this new system we propose, is able to take detailed logs about navigation events, continuously records any changes to the DOM, especially the interaction between JavaScript programs and the DOM, and dependencies between events of any type and the JavaScript callbacks, dependencies between pieces of JavaScript code loaded by the browser, compiled, and so on. And also, outside of recording all these details, we also provide a separate module that can do post-processing of the detailed logs provided by the browser, by our login system, so that we can abstract from the logs and provide a higher level representation in a form of an easier to interpret graph to the forensic analyst. And with that, I will let Bo explain the details of the system.
Okay, thanks, Professor Perdisci, for the introduction of JSgraph. Now let me talk about the JSgraph system part. So to efficiently record internal browsing events, we leverage and turn the Chromium, the dev tool. Specifically, we implement a new inspector agent, expanding the inspector instrumentation API to collect fine-grained information that is not otherwise gathered by existing dev tool agents. JSgraph continuously tracks DOM changes by monitoring the insertion and removal of DOM node, the modification of DOM attributes, and the creation of a child frame, and so on. So we also log JavaScript APIs to monitor the execution of script and the callbacks. When compiling the script, we log the script ID as well as the source code. We also log the script ID at the beginning and the end of the execution of the script and the callback functions. Those kind of information will be used to link later script execution and callbacks back to their definition source code. So we also log actual information for the callback to determine their registration scripts and events that targeting those kind of callbacks. Other critical events in the JavaScript, such as window.open, location.replace, XML HTTP requests, and so on, are also logged. So here is an example. Here's an example of implementation that we injected into the script compiling function to log the script ID and the source code. And there is the dumped log. So we can see that we recorded the script ID. And if the script is an external script, we will also record the URL. And here are other information, including the source code. We also provide an abstraction module that can automatically post-process the audit log into a higher level description. Here, we abstract user navigation, HTTP redirections, and JavaScript-driven navigation. We also abstract JavaScript code inclusion and execution, and JavaScript-driven DOM insertion, callback definition, and registration, and critical event execution. So let's take an example of the reconstruction of social engineering malware download attack. So remember that all the detailed file download event were captured in the JSgraph's audit log, such as the source URL of the download file. So the first step for the forensic analyst is to identify a group of suspicious download events. So forensic analyst will lead a all the download events recorded by JSgraph, narrows the navigation to a set of possible target machines, and identify time window of interest, for example, a time period right before the data leak, and select interesting file download logs as private points for analysts. So once this private point is selected, the analyst can use JSgraph's abstraction module to do a backward tracking automatically, which means we can work back in time automatically to reconstruct the sequence of audit logs. Here we only consider logs for events with direct path to the pivot points. For example, here we can see how the new window was opened by JavaScript using window.open, how the JavaScript performed the navigation using location.replace, and eventually redirect the user to the malware posting page. And let's move a little bit upper in the graph. We can also see here the user first search on Google and visit that video site. And while the script is loaded on that page and the callback is defined and registered by this script, when the user clicks on that video, the callback event was triggered. And here is the most interesting part. An empty iframe was injected into the DOM, and a piece of JavaScript was created and injected into that empty iframe. And this script will get executed and open the new window, as we saw in the previous slide. So if the forensic analyst is interested in what happened on the malware posting page, and JSgraph can also do a forward tracking automatically from the pivot point, which can help the analyst understand what happened within the page, what kind of event triggered the download of the malware, and so on. For explanation of this forward tracking figure, please refer to our paper. So in terms of performance overhead, we took advantage of Chromium's trace event infrastructure. We used trace event 0 to measure the time spent within a function, which will be used to measure the time overhead that our implementation introduced. And here is the example of how we measure the overhead taken to log the compiling of the script. We also use a trace event 0 begin 0 and end 0 to measure the execution time between two code points, which can be used to measure the baseline time. We measure the page load overhead, DOM construction overhead, JavaScript execution overhead, and overall overhead that we introduced by the JSgraph. And let's take the page load overhead, for example. Here we simply compute the start of the navigation of the page until the load event failed, which is the ending of the loading, the browser completes loading as the baseline. And we simply use that formula to compute the relative overhead. And for the details of other computation of other overheads, please refer to our paper. So we did multiple experiments for both Linux and Android. And we can see the overall medium overhead introduced by JSgraph is between 0.05 to 1.5%. And the 95 percentile is between 3.1% to 4.7%. While the page load overhead, the median page load overhead is between 3.2% to 3.9%, while the 95 percentile is between 5.7% to 8.2%. As for the storage overhead, take a Linux experiment, for example. We have like 50 minutes of active browsing, which produce 37 megabytes compressed logs, which is about 0.74 megabytes per minute. And if we extrapolate into the enterprise network, assuming 8 hours of browsing per day, 232 work days per year, and we will get less than 91 gigabytes of storage per user per year, and less than 91 terabytes to keep web audit log produced by 1,000 users for the entire year, which is definitely affordable by an enterprise. So to sum up, JSgraph record audit logs to enable detailed reconstruction of web security incidents. And like Chrome Peak, JSgraph is not limited to record the state of web pages only at the time of user actions. It also records the critical browser internal events, for example, the interaction between the JavaScript and the DOM. And it also provides a post-processing module to abstract audit log into easier to interpret graphs. And finally, it introduced acceptable performance and storage overhead. So that's all for the presentation. By the way, the binary of JSgraph is available on GitHub. And please download it and have a try. And the source code will also be available as soon as possible. So thank you so much. I'm ready to take any questions.
Any questions? So I had one. First off, a comment. I think it's really great that our program chairs put this talk in here and not in web security, because there's clearly so much overlap in what's happening in these papers, even though you're sort of at a different layer of the software stack. And what was my question? Let's see. Yes. So on that note, we saw that, in the 3 papers before yours in this session, we're struggling mightily at the system layer to combat things like dependency explosion or track the events that are actually of interest when we're doing these causal graphs. Did you find that when you were doing this JavaScript instrumentation that there was lots of, there were events that had high fan out, or there was, a lot of noise that made it difficult to find where the attack actually happens?
So I think in terms of web attacks, so it's different. So there are many representative nodes that we can look at. For example, in this paper, in the presentation, we see that we identified that the download of the malware as the pivot point. And this is one example. And we can also, depend on different attacks, we can define different kinds of formulas at the pivot point. For example, another example which we represent in our paper is the cross-site scripting attack, which we say that they are requiring the external URL, and there is a timer that, and also there is the schedule action event. So those kind of patterns, depend on different attacks, can be used to actually identify the point that to start with. And using our backward and forward tracking system, we can go to the entire trace that just related to this attack, but just ignore other noise.
I see. Yeah.
Just to add one more thing, I think you asked about the fan out, and we did see the fan out, especially so for the backward tracking. Things are a little bit easier because you find only the dependency that bring you directly to the pivot point. But for the forward tracking, we had an example of a case in which you really have a lot of nodes to take a look at.
Interesting.
After that.
All right, so maybe all of our authors in this session should get together and figure out what's applicable at the JavaScript layer that's happening at the system layer. I guess one more quick question. Oh no, go right ahead, please.
Will this work on general browsers like IE?
No, it's on Chromium.
So Chrome only? Okay.
I'll ask one. 85 gigabytes a year is, I believe, the number. So this is, by no means like a terrible place to be, but it also, adds up quite a bit. Is there more opportunity for, can we throw more things out? Do you think there's more opportunities to make this more efficient, or is this kind of, a practical minima?
Yeah, thank you for the good question. So I think in terms of enterprise, it's not a very, very big deal. This is the first point. And if we want to do something to reduce, we can actually whitelist some very known websites, and also filtering some scripts that we know is benign by the URL. So yeah, I guess we can definitely reduce some space. Yeah.
Great. Let's thank our speaker.
Thank you.